Another example of MC delta T, and this time I'll try to correct for heat loss by extrapolation. In this problem we have copper sulfate, a blue solution. We have it in a styrofoam cups. After 2 minutes we add our zinc when the temperature is not fluctuating. The reaction is single displacement, give you zinc sulfate, a transparent solution, plus precipitate of copper, which is red. Now, rather than just temperature minimum, temperature maximum, we are going to keep track of fluctuation of temperature versus time. Now, what this gives me a possibility that I have a graph like this. At this point, your maximum temperature has been reached. One of your reactant has been used up. The reaction is coming to completion. But what we like to do is extrapolate because the reaction is not instantaneous. So we're trying to compensate for heat loss. So we continue this best line of fit. You go to the last second that you added your zinc parallel to y-axis, and we are going to hit our extrapolated line. So what I'm saying is now we are compensating for the temperature. This difference here is what we like to be called delta T corrected. So delta T corrected is slightly higher than your maximum temperature compared to minimum, and it's 35.4 minus 25, so I'm getting about 10.4 degrees Celsius or Kelvin difference. That's my delta T. Now I'm ready to calculate heat of reaction first. So plug it into Q equal MC delta T. Assumption is this is a dilute solution, therefore all properties of water applies. Density is 1, therefore I have 50 grams of liquid water only. Heat capacity of water is used, 4.18 joules gram degree Kelvin or Celsius, times 10.4 degree Kelvin. Once we do that, we are going to get 2170 joules. We divide it by 1000, then we have 2.17 kilojoules. Now we need to find enthalpy, your energy involved per mole of reactant. So I need to find my moles of reactant that is limiting. So let's go after moles of zinc first. It's a solid, so it's mass divided by molar mass. So I have 1.2 grams of zinc. We look it up on the periodic table and you get to have 65.37 grams per mole for zinc. And when you do this division, you will get 0.0184 moles. Now let's do moles of Cu copper sulfate. Many times it's also written as just Cu2+. The two are exactly identical. It's an aqueous solution, so I need concentration times volume. Concentration is 0.2 mole per decimeter cube. The volume is 50 cm cube, which I take it 3 decimal places to the left. So 0.050 decimeter cube. When you do this, you get 0.01 as moles of 0.0100 moles of Cu. Therefore, this is the limiting reactant. It's 1 to 1. This is the smallest quantity. So I'm ready to calculate my delta H of reaction, which is heat divided by moles of reactant, limiting reactant. It's equal to 2.17 kilojoules divided by 0.0100 mole. It's 217 kilojoules per mole. Now don't forget to put your minus because the temperature was rising. It's an exothermic reaction. So in order to compensate for a reaction that is not instantaneous and you're losing heat, we are going to extrapolate and your temperature will be higher than before. This temperature does, if you go from maximum to minimum, you have not considered heat loss, and it will give you bigger % error.